Okay, so today we're going to talk about an alternative way to solve for power. So we've already talked about that the definition for power is equal to work divided by time, and the units that we use are watts. But we run into problems if we don't know what work was done or how much time it took. But we're going to make a new equation today, and we're going to build a new equation for power. So we're going to start with our power equals work over time, and we're going to use our definition for work. So we know that work is equal to force times displacement cosine theta. And we're going to assume that the force and the displacement are in the same direction, so theta is 0 and cosine theta is 1. So we have this divided by time. And hidden in here is something else that we know. We can see that we have distance divided by time. So what we get is that power is equal to force, and distance times divided by time is velocity. So we can solve for power by using force times velocity. So here's a problem. We're looking for power, and we're given mass, velocity, and a force, air resistance force value. So we can use our new equation. So our new equation is power equals force times velocity. The question is, what force do we need to use? Well, since we're talking about the power from the car, we need the engine force, which we're going to call capital E for engine. Well, how do we know what the engine force is? Same way we learned forces in the past. Anytime we dealt with forces, we drew a picture, and we need a free body diagram. So here's our car. We have gravity. We have normal force. It mentions this air resistance force of 800 newtons. So we have an air resistance force. So let's say that our car is traveling to the right. There's our car going that way. So air resistance force is going to oppose that. So we have resistance force, and we have engine force. How do we know what the engine force is going to be equal to? We're going to use sum of the forces equals mass times acceleration. And we're looking in the x. So I have engine minus resistance equals, it just says we're going 15 meters per second, so no acceleration. So acceleration is 0. So that means that the engine force equals the resistance force, which equals 800 newtons. So now we take our power equals FV. So we know that power equals engine force, 800 newtons, our velocity, 15 meters per second, and we get the power equal 12,000 watts. And are we done yet? Not quite, because we need horsepower, and we know that 1 horsepower is equal to 746 watts. So then we do 12,000 divided by 746, and we find out we need 160 horsepower to make this drive. So a good follow-up question is, how do we know what force to use for the engine force? And remember, the way that we did that is, first we drew a free body diagram. And then we use Newton's second law. Sum of the forces equals ma. And we solved for our new force, engine force equals. So in the previous example, we saw where the engine force making the car go forward was equal to the air resistance force back. But what else could be happening to this car so that the engine force maybe is not equal to the air resistance force? Well, remember that we used Newton's second law, sum of the forces equals ma, and we did have normal and gravity, but they're not in the direction of motion, so we weren't worried about them. And we had engine minus resistance, and in that case acceleration was 0. But If we actually have an acceleration, then that'll change this, and we'll have to go through and solve for that. So here we have another problem, what power, and since we're talking about a car, let's get this to horsepower. We know the mass of the car, and it says that it is accelerating from 15 to 20 meters per second in 6 seconds. So I'm going to draw my free body diagram, and I know for my car, I'm going to have a normal force up, gravity force down, engine force forward, and this doesn't mention air resistance at all. So my free body diagram is complete. So now I can go through and I use my new equation, power equals work over time, but work equals force times displacement over time, and displacement over time is V. So I can find what F is by using Newton's second law. Sum of the forces equals ma. Engine force is the only force, equals mass times acceleration. Well, the mass I have is given as 1,000 kilograms, but I don't have acceleration. So I have to go back into a chapter 2 problem. I know that V final equals V0 plus AT, so 30 equals 15 plus A times 6, which gives me the acceleration is 2.5 meters per second squared. And that can come up in here now. So I have 1,000 times 2.5, which gives me 2,500 newtons of force from my engine. And that then can come up here to my power equation. So I have 2,500. Now what speed do I need to use? Well, I'm going from 15 to 30 meters per second, so it could be anywhere in there, but I need to get all the way through this. And if I use kinematics, that means I'm using constant acceleration. So I got to make it through that very last piece of this. So I need to get it when I'm going 30 meters per second. 25 times 3 is 75. And then I have 3 zeros. Remember, that is watts. So I need to divide by 746 watts per horsepower. And that leaves me at just about 100 horsepower to make it through that acceleration. So here's that same problem again, and actually it's a kind of a combination of the last two, because now we want to know what the power is while we're accelerating, but there's also an air resistance force. So just to kind of give you a recap of remember how to do this, we have power equals work over time, and work is force times displacement over time, and displacement over time can be written as V, so power equals F of V. We need to find out what the force is. We do that by taking our car and drawing a free body diagram. And then we use that with the sum of the forces equals ma, and we have to solve for what our engine force is. Once we have our engine force, that's what we use for the force here, and then the velocity that we'll use is the greatest velocity in our acceleration, and then we can use that to solve for power. So hopefully that helps in solving for power when you're not given force, or when you're not given work and time, but a way to do it, changing work to force times displacement, and then doing power equals force times velocity.